Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom, including yesterday. Now, last night, I had a little bit of a snafu, and I was recording a video. I put it up online, about a half hour's worth of recording with no audio. And I'm not going to let my frustration show here. I was livid. It's hard to be able to do that and see that all of that, I don't know if it went to waste, because you can see that some of it, I actually wrote some things down, but I'm going to have that feeling of I have to recreate that now. Good thing I didn't go through the entire thing and then realize it after. I'm looking right now, my microphone levels are actually working. I'm surprised I didn't look at it before and just see that it wasn't there. Anyway, I'm going to be doing with you guys an overview of everything that we've been doing for the past while, 5 or 6 weeks or so, involving just quadratics as of recent, quadratics, cubics, and factoring them. A lot of things involving that. Not solving any quadratics, none of the zero product property things from before, but just factoring them down. And the strategies involved with that, as well as dividing them. We did some things with division. And then before that, we did things with transformations of polynomials, whether they were cubics, quadratics, larger ones in factored form, inverses, even odd functions, which I don't believe is actually going to be involved in what I'm going to do in this overview here. And there's at least one more thing. I can't think of what it actually is right now. So, well, you know what? We'll get into it when we do. Okay, so with all that stuff involved, I wanted to just let you know right now. This was a practice exam that was given to me from a colleague, and it was something, as a just quick overview, I said, hey, you know what, looks pretty good. And I decided to go through it myself first. So I did a time trial. I did a time trial myself, and you'll see a nice sped up version of it, a time-lapse version, if you will. And you'll see that I did it in 14 minutes, 5 seconds. That was a pretty nice time to do. It's 30 questions, by the way, 14 minutes and 5 seconds. So that was pretty fun. But going through it, I noticed that there were some things that, there are some frills and such that I'm going to amend, change, or append, rather, even add on to some things that I want to decide to do in ways that I didn't even do in the version that I did. And there's a problem that I think I even want to change as well. So when it comes to all that, guys, just, composition with functions. I want to do that involved with the inverse things as well. So I'm going to do a bunch of things along the way, guys. I know that if I did that in 14 minutes, 5 seconds, this thing's probably going to take over an hour. So if you don't mind it, guys, check out the PDF down below where you can find this thing in the description section, and timestamps for each problem if I can get them up for you and with you. So without further ado, guys, I'm going to go ahead and get started, and we're going to look at the first two problems here as I redo some of the problems that I did in the past. And let's go ahead and get started. Number one, let's subtract a polynomial minus a polynomial, trinomials, if you will. And in subtracting here, remember, this isn't distribution of everything and multiplying. We are subtracting this quantity, though, which means we will distribute the negative. And in distributing the negative here, we will change all of these signs. And let's go ahead and write everything without parentheses so we can properly combine like terms. And, oh, by the way, write this in standard form. That should never go away. So I have 5k to the fourth here, plus 5 plus k squared. Those leave unchanged as they are multiplying essentially by a positive 1. And right here, these are essentially multiplying by a negative 1. So every sign changes. We get negative 4k squared plus 2k to the fourth. Had some salad. Plus 7. So now we combine like terms, and like I said, I want to get things in standard form. I have 5k to the fourth here, plus 2k to the fourth here. That'll give us 7k to the fourth power. I have k squared minus 4k squared is negative 3k squared, and that leaves us with the constants of 5 plus 7, which is 12. That is in proper standard form here, degree 4, 2, and 0, and we are good. We won't, by the way, if these were factorable, I don't know if it is or not, but we aren't going to factor it any deeper. Simplifying is actually the opposite of factoring. Simplifying is no parentheses, combine like terms, do all that kind of stuff. Factoring, yeah, that's actually not simplifying. If I asked you to factor, awesome, but I don't know if it's factorable, and I'm not going to try. All right, number 2. 1 plus 5 n squared minus 4 is very much the same, even down to subtraction. So let's write this again without parentheses as to get the proper signs as they'll be, as those stay the same here. When I distribute the negative, I'll get a negative 5n squared minus positive n cubed minus 2n. So all of these turn into negatives, and keep in mind subtracting a negative will be a positive, which we'll see again when we do polynomial long division. All right, combine like terms here. Our largest degree here is the cubic. So I have negative 4n cubed minus 1n cubed. That'll be negative 5n cubed. And then we have a 5n squared minus 5n squared. That's it. So those cancel out. That's 0n squared. Don't write that as n squared. That's not n squared. It's 0n squared, which is 0. N squared would be 1n squared for something like 5n squared minus 4n squared. I feel like I just said n squared a whole lot, so I'm going to stop saying n squared. Minus 2n, no combination, plus 1. And that's it. So that's our standard form right there in combining like terms. All right, there we go. There are the two subtraction problems, and we move forward into 3 through 6, find each product. You know, one thing I want to mention about this PDF right here, if you decide to download it, use it, what have you, is they don't give you a lot of room. Now, I know when I did these problems, I gave myself the room that I needed. I think in the division problems, I even separated the 7 and 8, I think the number 7, the ones after this, vertically, and I just went downward vertical. And I'll be doing the same thing here again when I work it out. So not much room here. If you want to do this on a separate sheet of paper, that's great. Like on numbers 3 through 6, I'm just going to go ahead and do them down here for you. So on number 3, we have 8b minus 5 times 6b minus 6. This is now multiplication. We will now distribute these, or FOIL, if you will. First, outside, inside, last. First, we do 8b times 6b, which is 48b squared. Remember the b times b. 8b times negative 6 is negative 48b. Negative 5 times 6b is negative 30b. And negative 5 times negative 6, remember it's still a negative 5, is positive 30. Okay, and then we have to combine like terms. We're going to have these middle terms here combine. Negative 48b minus 30b is negative 78b. So this will equal 48b squared minus 78b plus 30. All right, and that is the final result of that one there. All right, number 4, let's, I guess, down here. So we have 8x plus 1 times 7x plus 6. Once again, FOIL. Distribute here, multiply. 8x times 7x is 56x squared. 8x times 6 is 48x. 1 times 7x is 7x, and 1 times 6 is 6. And we combine like terms here. We'll get 56x squared plus 55x plus 6. There we go. All right. There is number 4. Number 5. Number 5, no longer FOIL. It's a binomial times a trinomial. We have to make sure that, of course, we multiply each term in one quantity by every term in the other quantity. So 2v will multiply with the 7v squared, the 8v, and the 3. And the 3 will multiply with 7v squared, 8v, and 3. So I'm definitely going to write all 6 of these terms out, and then I have to combine like terms after and keep it in standard form, as we would before. Just a little bit more to organize. So 2v times 7v squared, guys, that is 14v cubed. And then 2v times 8v will be 16v squared. 2v times 3 is 6v. And then we have 3 times 7v squared there, which is 21v squared. And then plus, looks like it's going to be 24v and 9. All right, so now we combine like terms here. And again, let's keep it in standard form. This v cubed will stand alone here, 14v cubed. That is not combining with anything. The 16v squared adds with 21v squared, and we get 37v squared. Let's find the v's now. 6v plus 24v is 30v. And then plus 9, that is unaffected by anything else, and that is the result of that guy there for number 5. And number 6, we have another binomial times trinomial here. So once again, distribution. Can I go without the arrows here? Would it make sense that I do 5a times those things? Sure, let's go ahead and do that. So number 6 here, hold on. Let's do, that is 10a cubed plus 40a squared minus 5a. And now the negative 7 is going to multiply with all 3. And remember, it is a negative 7 that's applied to all 3 there. So negative 14a squared, and then minus 56a, and then plus 7. Negative 7 times negative 1 is plus 7. Okay, so you combine all those. Again, the a cubed is by itself, doesn't combine with anything. 40a squared minus 14a squared, I believe, is 26a squared. Negative 5a minus 56a is negative 61a, and then plus 7. All right, So those are numbers 5 through 6, and there's distribution in a nutshell. Everything else that you're going to see from here is division slash factoring when it comes to the module involved with all these polynomials here. That was the basic stuff kind of leading into it. Let's go forward. So now we're going to divide, guys, and I am going to go ahead and I will use long division and synthetic division, both of them, so you have an idea. Now, one heads up about this. If you saw my video with dividing things, guys, I did ones that had 0 remainders. It was purposely for my students to give them an idea that they'll know that they divided correctly if they got a remainder of 0. At least it's unlikely they landed on a false positive, so despite my solution guide video, I didn't do that. These two do have remainders. I know this because I already did the problems yesterday. And then I did them again without being recorded and capture my audio. But that being said, I'll show you how the remainder thing works. It's not a terrible thing. It's just the idea of it. Just warning you that the remainders will come and you didn't do anything wrong if you got a remainder. Anyway, I'm going to use both long division and synthetic division on this thing here. Let's start with long division. X to the 5th plus 7x to the 4th plus 9x cubed plus 19x squared plus 11x plus 34. Let's divide that all by x plus 6. And I'm going to do this mostly with the large idea that you've seen me do this before. I'll give you some reminders about how I subtract and such, but we take the leading term here and see how many times it goes into the leading term here. X goes into x to the 5th, x to the 4th times. And we know that because when we do x times x to the 4th, we get x to the 5th, which is exactly what we expect. We want these things to cancel. If they don't cancel when we subtract, something went wrong. 6 times x to the 4th is 6x to the 4th. And I'm going to write it underneath the 7x to the 4th because I want to combine like terms there. Now this will subtract, and if you recall, I don't write the subtraction sign myself. It's just a me thing. But x to the 5th minus x to the 5th is 0. Those are gone. 7x to the 4th minus 6x to the 4th is 1x to the 4th. And I'm going to bring down the rest of these guys as they're subtracting 0. Therefore, they are just a part of it. Let's come on down. And I'm going to do x plus 6 again. Let's see how many times x goes into x to the 4th. Just once with a little x to the 3rd there. X times x cubed is x to the 4th. How fitting. 6 times x cubed is 6x cubed. And let's go ahead and subtract again. All of these are pluses. It's going to make for a nice little clean thing when we subtract. We kind of know what we expect there. 9x cubed minus 6x cubed is 3x cubed. And we got a 19x squared, 11x, and 34. Let's go ahead and divide. Let's just keep going down. X goes into 3x cubed. 3x squared times, as x times 3x squared is 3x cubed. 6 times 3x squared is 18x squared. And as we subtract there, 0. And 1x squared, as I reminded you. 19x squared minus 19x squared would be 0x squared, but which is 0. But 19x squared minus 18x squared is 1x squared, or just x squared. All right, let's go. Let's go. X goes into x squared, just x times. 1x times x is x squared. 6 times x is 6x. Let's subtract ahoy mahoy. And we get 5x plus 34. And yep, looks like we're going to have a nice fancy remainder here. X goes into 5x 5 times, but 6 times 5 is just 30, not quite 34. And we subtract and we get a remainder of 4. So this is the quotient, this is the remainder. How would we write that out? Now, what I had us practice in my last video was the concept of what this dividend would factor into, which would be the divisor times the quotient, I guess, with a remainder involved, which I'm not really working with here. Now let's just look at what the division's answer is, which you can kind of see it in two forms here with quotient and remainder, but let's write it all as one line here. So what is this divided by this equal to? Well, it's equal to x to the 4th plus x cubed plus 3x squared plus x plus 5. And there's a remainder of 4. Now, how do remainders work? Well, the idea of the remainder, guys, if you keep in mind, I would have checked to see how many times x goes into 4. X can't go into 4 any whole number of times because there are no degrees of x involved with the 4. So, excuse me, 4 doesn't divide fully into x plus 6. If it doesn't, that's what makes a remainder. But if it doesn't, we write it as 4 over x plus 6. Remember, all of these were something over x plus 6, but we divided them out to get this quotient. Not all of these, but what the original thing was. We divided out to get this quotient. The 4 never did divide by the x plus 6, and this is how it remains. That's just the final answer. That's how that works. Now, when I test my own kiddos, they're going to have a 0 remainder. I'll make sure of that because it's just, something they haven't really worked with. I just want to make sure that when they divide it, they kind of know they did. See, they won't know if they did this correctly or not. And not to say that remainders don't have their purpose. They actually very much do. They are extremely important when it comes to what you do with them in pre-calculus and in calculus and such, involving asymptotes and all that nature. But what I'm doing with my kiddos here is just the idea of, well, I want to know that you know how to do the division correctly, and you'll know that you did the division correctly if you get a 0 remainder. All right, so let's go ahead and do synthetic division on this guy as well. So I got to rewrite that whole thing here, x to the 5th plus 7x to the 4th plus 9x cubed. All right. So synthetic division is something that, remember, you can only do if you're dividing by a linear factor in like the x plus a or x minus a form, whichever you want to call it. In this case, this is that because we have an x plus 6 here. So this is possible to do. I love synthetic division, but furthermore, I also understand why we can do it and when we can do it and therefore how it's done. So if you understand it, at least in the streamlined fashion that it is, that's good. So what we do here, because this is just dividing, and again, this is assuming that you are dividing by a linear factor. If you're not, you can't do it the way that it kind of wants you to. With this x plus 6, negative 6 is considered the root of this thing, and we are going to place a nice negative 6 up in the upper left corner. And I'm going to write the coefficients of all these as we descend a single degree in this polynomial here. So 1, x to the 5th, 7x to the 4th, 9x cubed, 19x squared, 11x, and 34 as the constant. And we are going to do a combination of multiplying and adding, also with bringing a value down. This 1 is going to be brought down just naturally. It is as the result of how things work here. And every number that's down here is going to multiply by this number here. And it's going to be, that product's going to move up here. So 1 times negative 6 is negative 6. Let's add these. 7 plus negative 6 is 7 minus 6, which is 1. 1 times negative 6 is negative 6. 9 minus 6 is 3. 3 times negative 6 is negative 18. 19 minus 18 is 1. 1 times negative 6 is negative 6. 11 minus 6 is 5. 5 times negative 6 is negative 30. 34 minus 30 is 4. Okay. Pardon me. So here's how the result comes out. 4 ends up being the remainder. And we can kind of understand this because as we had the quintic, quartic, cubic, quadratic, linear, and constant terms, and then we divided by a degree of x, everything should diminish a single degree. The x to the 5th now diminishes here. We should see an x to the 4th and an x cubed, squared, x to the 1st power, constant. And then a constant divided by the x would leave with the remainder. That's what we saw before here. So 4 is the remainder. And if that's the remainder, then again, it's constant, linear, quadratic, cubic, quartic. So what we're going to do is, as this was an x to the 5th, this is now an x to the 4th, 1x to the 4th, 1x cubed, 3x squared, 1x to the 1st, and 5. And the remainder is 4 over that there, x plus 6. So we should get the same answer here as we got right here. Let's check it out. X to the 4th, x cubed, 3x squared, x 5, and 4 over x to the 6th, x plus 6, excuse me. You can see how much just kind of faster it is, at least how much more compact it is, streamlined, not a bunch of these x's, and look at that in comparison. I'm not disparaging long division at all. In fact, it's something that you'll have to do in situations. You can always use synthetic division, but synthetic division has its place, and I would argue this is its place. But, use long division as much as you can, as often as you can. You need to know this one. It's good to know this one in its instances, and this is one of them. All right, so here we go. Number 8. Let's do the same thing. Long division, synthetic division. Let's get x to the 5th, 10x to the 4th. So I'm going to do both again here. By the way, time-wise, if we consider that it took me the 14 minutes to do the things, I'm now at the 19-minute mark for this video. So 5 minutes passed having done it, and I'm only on question 8. I've only done 7 questions. There are 30 questions here. So you can imagine, guys, this will not be, one of them short skis, right? This is not going to be a short video, as it's a nice overview of 2 modules with a lot of stuff involved, right? These division things, as I do them twice, obviously, will take quite a bit to do as well. Give me a moment here. I'm going to move myself. Whee! All right. So move myself over here. Let's do this long division. X goes into x to the 5th, x to the 4th times x to the 4th is x to the 5th. Negative 5 times x to the fourth is negative 5x to the fourth. Now here's where you got to be careful involving subtraction, especially not if you're me, but if you're following my style. I'll remember to do this myself. I am subtracting this minus this is 0, but this minus this, be careful. Negative minus negative becomes a negative, this, and plus. I'm not going to write the plus, I just know it's going to happen. Negative 10x to the fourth minus negative 5x to the fourth is negative 5x to the fourth. Again, subtracting the negative becomes addition. And then the rest goes down there. So really, really, really do be careful with these things. Make sure that you're subtracting each time when you do it. And as my students once again know, you'll get a 0 remainder if you did everything correctly. At least I don't assume any false positives. X times what is negative 5x to the fourth? That should be negative 5x cubed. And multiply those, we get negative 5x to the fourth there. And then plus negative times negative, 25x cubed. So yeah, this long division comes out in a nifty fashion there. Subtract, we get 7x cubed. 7x cubed minus 36x squared plus 9x minus 30. All right, x minus 5. And, really do compare how long the long division here takes to the synthetic division, just to convince you that it's worth knowing that other one when the time comes. X goes into 7x cubed, 7x squared times. And we get 7x cubed there. And then it looks like minus 35. Whoop. Minus. It looks weird seeing my 7 like this. I used to write it like this back in the day all the time. It looks really weird for me to see my 7 like that. It looks very barren and naked. Negative 5 times 7x squared is negative 35x squared. All right, here we go. Right, brand new, exciting video, guys. I have to keep this exciting for you guys. All right, negative minus a negative is negative plus, so we get a negative 1x squared there. And then plus 9x minus 30. Yeah, I don't know if I live up to the brand new video for sure. Are these exciting? I don't know. I sure hope they're exciting for you. Am I excited to do math? I think I have to say that by law as a math teacher. I'm sure there are other ways that I could cite you in video form with these things. Negative 5 times negative x is a positive 5x. Hopefully you're okay with me speaking over what we just did there as like, this is an important math lesson you're doing, Mr. Robinson. I got to keep it brand new and exciting. All right, negative x squared minus negative x squared is 0. 9x minus 5x is 4x. All right, here we go. Last bit. X goes into 4x 4 times. X times 4 is 4x. Negative 5 times 4 is negative 20. Cancel, and negative 30 minus negative 20 is negative 10. X minus 5 does not go into negative 10 any number of times there. That is the remainder. Again, when you get down to a constant, when you're dividing by something of a higher degree, that ends up being the remainder there. Not just if you get 0, it's remainder. You have to kind of remember that. All right, so this division here, this divided by this, its quotient, or its final result, I should say, is the quotient kind of plus how that remainder works. So that divided by that equals, let's check this out, that is this part, x to the fourth minus 5x cubed plus 7x squared minus x plus 4. And then the remainder of negative 10. Now, it's a negative, so I'm going to say minus, and then 10 divides by that x minus 5, as it could never divide wholly. Straight up. There we go. Awesome. Okay. Yeah, you definitely couldn't fit this on that paper. This is definitely something you would have had to have manufactured on a separate sheet of paper, or maybe with synthetic division. I don't know how small you can write and how much it can fit. Let's go ahead and rewrite this down here again as I do synthetic division on this problem. Plus 32x cubed. And like I said, let's see how fast this kind of goes after this, and you'll possibly be encouraged to consider learning this as a problem calls for it when you're allowed to use it. X minus 5. Okay, you just don't want to mess it up either. All right, so with the x minus 5 factor, 5 ends up being your root. It really is the opposite sign. If x minus 5 equals 0, then x equals 5. Let's list the coefficients here. There are some other things with coefficients that I've mentioned in the other video and I warned you about, things you got to be careful with, such as placeholder values. But these seem to go down in descending order of degree perfectly, so I don't need to place any zeros here. All right, let's do it. Bring down the 1. 1 times 5 is 5. Negative 10 plus 5 is negative 5. I'll slow down a little bit. I'm sure you're following along and you'd like to write as well. Negative 5 times 5 is negative 25. 32 minus 25 is 7. Now, by the way, keep this in mind, guys. In long division, I need to mention this. In long division, we are subtracting. Despite the fact I'm not writing the subtraction, we are subtracting. That's because this is still a negative 5 that happens as we subtract. Now it's a positive 5. As I switch that sign, we switch our subtraction to addition. This is adding. That was subtracting. I hope that makes sense. And when I say adding here, I mean adding the negative. 7 times 5 is 35. Negative 36 plus 35 is negative 1. We get negative 5 there. 9 minus 5 is 4. And 20, and negative 30 plus 20 is negative 10. So we get a remainder right there of negative 10. Here's our constant, linear, quadratic, cubic, quartic. We were at x to the fifth. Now we're x to the fourth as we divided by a power of x. So x to the fourth minus 5x cubed plus 7x squared minus x plus 4. A remainder of negative 10 is minus 10 over x minus 5. All right, let's see if we got the same answer here. Let's see if it all cleaned up. Check, 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 and check. All working out there. Awesome, guys. So that was the long division section, whether we use actually long division or synthetic division. And let's go ahead and move forward. Okay, now we're going to factor completely. The next 14, I think, problems here are all factoring. These are kind of interesting because to me they go in like reverse order. This was like the most recent thing I'd say that I taught when it came to factoring, so I hope you're okay with that nature, that's what's happening here. And also because the nature of these problems, there are 8 of them. I don't know if I can fit them all down below and make it easier. I think I'll fit it within here. I did do that when I made the video myself, I believe, so I'm going to stick to that. So these first ones here, guys, we have quadrinomial. How do we factor that thing? We work on factoring by grouping. Assuming it is factorable, which it is, we can pair up these two guys and these two guys. You can always do this, by the way, as long as your pairs are split up to proper factorization. And we can check and see here what the greatest common factor is of these two terms, which is 8r squared. You're left with a 2r minus 3 if you factor that out completely. And then right here, you know, there's no greatest common factor, so to speak, except for 1. But, darn it, let's factor out that 1. Plus 1 times 2r minus 3. Our goal in this factoring by grouping is we find the greatest common factor of each pair, and in turn, we will then seek that this here should be an identical pair of items that can factor out of the 8r squared and the 1 product term things. So we factor out 2r minus 3 and 8r squared plus 1 remains. So we have 8r squared plus 1 times 2r minus 3, and that is the factorization of this. Don't believe me? Double check it. Foil this back out. We get 16r cubed minus 24r squared plus 2r minus 3. And there's the factoring by grouping that seems to take hold, quite lovingly so. All right, number 10, another factoring by grouping problem. Common factor here, common factor here. 8p cubed minus 8p squared. It looks like 8p squared is a common factor. It doesn't look much different from that. And we're left with, it looks like a p minus, a 1 there, right? Same thing I was talking about with this one, right? We got to write it. It's a part of what happens there. It's not like it's invisible. Neither is that negative one. Now here, we do have to factor out not just the 5, obviously, but the negative. Our goal is to get p minus 1 inside this thing, if you can imagine that. And we always factor out leading negative terms for great reason, because we want this thing to be positive inside, and as it's going to match right here. Factor out the negative 5, you are left with p minus 1. That is important, crucial. So over here, this will equal, factor out the p minus 1 from both of these, you're left with 8p squared minus 5, and p minus 1. Now, I think it's worth making mention now, before I continue, that, in factoring these, it is possible. It is very possible that, especially given the quadratic nature of these parts here, that you can be looking at some point, something else that is further factorable. And I don't just mean greatest common factor further factorable. I mean a quadratic, like a difference of 2 squares. And, it's possible here. Consider the fact that this could potentially be a difference of 2 squares because of the quadratic, the constant, and the minus. This one's not. This one was very close. If this was 9r, well, I guess it'd have to be a minus right here. But, this could be a difference of 2 squares. So look for your perfect square values. Make sure you know what they are. Have them call to you. And then factor it more deeply if possible. When they say factor completely, we spare no expense on that. We got to make sure we factor fully whenever we can. All right, like number 11, for example. This is a sum of 2 cubes. This is our a cubed plus b cubed nature, as in a cubed plus b cubed. And in a cubed plus b cubed form as it stands, guys, that's going to factor into a plus b times a squared, I'll go back to that if we have to, minus a times b plus b squared. So let's look at that, let's look at that again. 3x quantity cubed is 27x cubed. 3 cubed is 27, x cubed is x cubed, and then there's the 1 cubed. That's our a cubed plus b cubed format. We can kind of recognize it for what it is. They're not very often you see any other problems asked to factor that don't take on that form. Anyway, here's our a plus b. Now a squared, we square the 3 and square the x. Keep that in mind. This will be a minus as we do a times b, 3x times 1, and plus 1 squared is 1. And that's the final factorization. This quadratic right here can never factor farther down. Outside of greatest common factors that we should have already pulled out, this quadratic cannot factor down more deeply in a sum of 2 cubes, difference of 2 cubes. Never can, never will. Just kind of keep that in mind as we continue forward. All right, this 3a cubed minus 192 sure looks like it wants to be a difference of 2 cubes, but 3 and 192 aren't perfect cubes. Common factor, right? We always seek those. Common factor of 3. A cubed minus, I believe that to be 64. Yeah, that should be. And yeah, okay, this looks more like a difference of 2 cubes here. A cubed minus 64. Because here we're cubing, oh, I don't know, a. And here we're cubing 4. Right? So, not that this is the factorization. This is the step, of course not required, that kind of gives you that recognition of here's our a cubed minus b cubed. Literally a cubed here. I don't have to change anything in that part of the formula. So as the 3 stands outside, a cubed minus b cubed factors to a minus b times a squared, again literally, plus ab, so a times 4, 4a, plus b squared, which is 16. And there's your final factorization. And once more, guys, this quadratic can never factor down further. So you are done. We got the greatest common factor first. You got to get into that to even recognize the rest. So yeah, hey, always look for greatest common factors. I've never lost sight of talking to you about that. Okay, let's keep moving forward here. We have number 13, 2x to the 4th minus 21x squared plus 49. Now this one takes on its quadratic form. First of all, no common factors here. Now this one takes on its quadratic form. Is it a quadratic itself? No. Well, sort of. It's a quartic, but something is being squared, right? X squared is being squared. X squared is being raised to the first power here. It's got that quadratic nature. We can still break it down into like a binomial times a binomial, work some things out, but instead of having an x and an x, it'll be an x squared and an x squared. Sometimes we use U substitution. We've kind of brought that up before. I think I'm kind of skipping past that now, something that I don't necessarily do. I do it in calculus, given the kinds of problems we're doing here. But here's what I know. I know this will be some sort of x squared times x squared. And furthermore, as we're playing as normal factoring now, I know this is some sort of 2x squared times x squared. Only way I'm going to get 2x to the 4th here and a nice little x squared going on here. So we got a positive product and a negative sum. That means we also know a minus here. We got to work out some factors of 49 that over the course of foiling here, this times this plus this times this, we get a negative 21. I am definitely a lot less inclined to be looking at 49 times 1 as I am at 7 times 7, mostly because that 21 is not as large as 49. I don't generally look at the largest factor version of this unless I'm really seeing a big number take play here. I'm just going to ignore it. It's not going to work. Let's try the 7 and 7 that probably kind of has to work here if it's factorable, and I think all of these should be. So we got negative 14 minus 7. And when I say negative 14, I mean 2 times negative 7. And when I say minus 7, I mean negative 7 times this invisible 1. So negative 14 minus 7 is negative 21. Hey, there's the factorization. Now, I preach for my students to be efficient on this. And yo, kiddos, if you're listening to this, work to be efficient on these. Factoring will not go away in the next things that we do when we simplify rational expressions. And I am not going to wait around for you to say, hold on a second, and you're doing some other form that your tutor taught you or something like that. No, let's work. Let's work. I tested one thing, and that was it. I spoke over it for a long time, but remember, I did this thing in 14 minutes, 5 seconds. This part was probably pretty fast. You got to make sure that you're working toward being efficient. There's more to be done than just the factorization when we do. By the way, before I continue on the next problem, look deeply and make sure you don't have a difference of 2 squares, y'all. We don't. If this was like a 9, it would be a difference of 2 squares. It's not, but check it out because they're possible. Actually, all these are possible. These are all to the 4th power, right? Let's keep going. 5m to the 4th minus 39m squared plus 54. Once again, if this is factorable, we're looking at some sort of m squared times m squared. In this case, because 5 is a prime number, we know it's some sort of 5m squared times m squared. We have another positive product, negative sum here, so we got another minus going. Now, 54 54 here being a composite number, well, so was 49, but you have several more. I don't know if several more. We do have a few more things to look at if you consider these with me, guys. We have a possibility of 54 times 1, 27 and 2. It's something in 3, yeah? Yeah, 18 and 3. 18 and 3. 4, no. 5, no. 6, 9, and 6. And I think that's the extent. So we have several more to consider here. One thing that's not going to help us drastically, that's not going to help us drastically here is, each of these is an even times an odd. And you know how I kind of like to look at and talk about this odd kind of thing going on with these. And it's not going to be very possible for us to look at what should go where. There is no common factor with 5. There is no... any of these are possible outside of the idea that something's too large and small. So this is one where there would be a little more testing going on, including swapping values. I'll tell you what can't work. The 54 and 1. That is too large. 54 already being larger than the 39, as we don't go back to 39, means it's not worth testing. 27 is only possible worth testing if you put it here. You can't put it with the 5, because 5 times 27 would just be too big. In fact, 5 shouldn't work with any of these ones. I shouldn't put the 27, the 18, or the 9 here. It would get too large. 5 times 9 itself is 45. So I'm going to try this one, and this one, and this one here, and see which ones end up working. So 5 times, so this is negative 10 minus 27, and that's negative 39. That one is 2. Let's see, I see my answer as I work on it. But that's, it's close. It's close, but it's not it. It's not it. Let's try the 3. Let's see, the 3 and the 18. That's negative 15 minus 18. That's negative 33. No, that didn't seem to work. And now let's try the 9 and the 6. And remember, place the 6 over here in the 9. That'll be negative 30 minus 9. That's negative 39. So this one did seem to work out, guys. Look, I only did test 3 in the end. Now, again, if you see me do work this out, I do it most of it mentally. I'm just picturing it, see what works. I go, negative 37, no. Negative, whatever it was. No. Negative 33, negative 39, yes. So I tested 3 of them when 8 were possible, right? And that was without any of the even odd talk or a common factor talk. So that was still a nice go. Okay, number 15. 6m to the 4th minus 3m squared minus 84. I am sensing a common factor of 3 here, which we can look into. So if I factor 3 out, I'm going to get 2m to the 4th minus 1m squared minus 28, I think. So 3 here. So now we're going to get a 2m squared times an m squared, as that's a nice little prime number again. Now with a negative product, I don't know. I mean, I know plus minus. I don't know which direction it goes yet. All right, so we got to kind of work that out. Now 28, let's list those factors here to kind of just give you what we're going to possibly consider. So 28 times 1, 14 times 2, nothing times 3, and 7 times 4, all possibles there. Now 28 and 1, or excuse me, let me backtrack a little bit. This is an odd number here. Okay, this is an odd number here. We're going to have to work some even plus odd scenario. That means the 2 evens are out. And I can't work 28 or 4 in this portion with 2. So, okay, so listen to this one. I can't work 28 or 4 with this portion of 2, right? If I put 28 or 4 here, I have a common factor of 2 that shouldn't exist. So those are gone. But I can't put 28 here either because that's just too large. So that leaves me really with one possibility, which is 4 and 7. There's no other possibility that I'd be looking at there. Everything else was either a greatest common factor or too large or the evens. So I'm just left with this possibility. Let's check it out. Negative 8 plus 7. And that's negative 1. Now listen, I could have gotten a positive 1, and then I would just switch these signs. But this was a negative 1. This worked out. And, I'm not going to box this answer, though. If you notice this here, guys, we have a difference of 2 squares in m squared minus 4. So this will factor into m plus 2 times m minus 2. Hopefully the difference of 2 squares thing kind of works itself. A plus b times a minus b there. So there's the factorization of that. And yeah, once again, I only tested one thing. That's being efficient. That's being efficient. Nothing else was ever even considered. All right, here we go. 7u to the 4th plus 5u squared minus 18. No common factors. but let's go ahead and work that out. 7u squared and u squared. I guess we've been relatively blessed only having prime numbers here, nothing else to test. But whenever I play with that even odd stuff, you know that I can generally try and break something down that we would eliminate anyway, which is something I wish we got to talk about. All right, positive product, negative sum. Let's try the plus minus and see where we go from there. 18, just to list them out here, we have 18 times 1, 9 times 2, and 6 times 3. Okay. Now, all these are combinations of even odds. So we have an odd number here. Looks like anything could potentially be tested under the sun. Now, 7 times 18 would be too large here, but it's maybe worth trying that 18 and 1 on this side. So let's try that out. Negative 7 plus 18. No, that's 11. Okay, let's discard those. 7 times 9 it would be too large for there. So let's try the 2 with the 9 here. That's negative 14 plus 9. Okay, that's negative 5. That's negative 5, and we need a positive 5. So that means we got to swap the minus and the plus here, or the plus and the minus to minus and plus, like that. And it looks like that's our answer. Again, that's 14 minus 9, and that's 5. So the second thing I tried, there was a possibility of, 7 times 6 would have been too big. That I could have tried 7 times 3, and, that wouldn't have worked. But there we go. So I would have tested it. I tested two things. I would have tested as many as 3, and I stopped on the second one. Good efficiency, no difference of 2 squares, and we move forward. We still have 6 more problems to factor here. So factor each. I still have a, by the way, this thing might say equals 0 on the PDF. I apologize for that. We're just doing straight up factoring, not solving. I wish we were solving, but that's okay. Let's move forward. X cubed minus 1. This is your a cubed minus b cubed scenario. X cubed minus 1 cubed. And that'll factor into x minus 1 times x squared plus x times 1 plus 1 squared. And that's it. Here we have another one of those things. Although, keep in mind, these are now easier problems, if you will. This is one of those things, but it's a 1x squared now, right? So right here, when we factor this one, it's an x squared times x squared, yeah. But in this case here, we just got to figure out plus plus. What two numbers multiply to make 42 and add to make 13? That looks like 6 and 7. Naturally, it's the first multiplication I want to try and do. I don't like to go to, again, 42 and 1, 20, 21 and 2, 14 and 3. I like to go to the obvious multiplications that I just know, just to get it out of the way if it's wrong, right? Plus 13 is not too big of a number. Any of those other things I think already would have just knocked it out. 14 and 3 already. 14 is too big. So looks like that works out. There's no sum of 2 squares thing that exists, and this wouldn't be a sum of 2 squares even if it did exist. So there's 17 and 18. We got 4 more factoring. These are quadratic straight up as we look for common factors and such. I get to talk strategy with you guys again as we move forward on these. All right, 9x squared minus 10x plus 1. I already see the answer here. But so 9x squared has a possibility of 9x times x or 3x times 3x. Let me just get the 3x times 3x out of the way and the conversation to be had with that. You know what's actually good news about this problem, including the 3x and 3x? The only possibility of this being 3x and 3x, keep in mind, this is a 1. It's a 1, and with a negative here, that means this will be minus 1, minus 1. This would be indicative of a perfect square trinomial, right? It's 3x minus 1 quantity squared. And this isn't a perfect square trinomial because negative 10 isn't double the product of 3x and negative 1. This would be a perfect square trinomial, and I would have recognized that immediately. But this one's not. So I already know this is the only possibility for it, so I know that's not it. The only other possibility, guys, and again, this is good news because of the 1. The 1 means this has to be minus 1, minus 1. There's no other option. Not even plus 1, because that tends negative. So if this doesn't work, nothing does. Negative 9x minus 1x is negative 10x, and that's it. That is the factorization. Good strategies to play with there. All right. And, that's why I said I saw it immediately. There really wasn't any other option for me to play with there. All right, number 20. No common factors here, but, we are dealing with, it looks like all these are composite numbers here. The 10x squared. 10 can come from 10 times 1 or 5 times 2. So, given that it's both even odd here, there's not really any knowledge to play with as far as how we can separate and determine this shouldn't be what it is. So it's worth possibly considering testing everything. 10x and x here. Now there's a plus minus involved, and 14 comes from 14 times 1 and 7 times 2. If anything, guys, strategically I have I have only very little to work with as far as telling you what I can avoid. I can avoid common factor bases, like the 14 and 2 shouldn't go with the 10 because that would give me a common factor. So the only things I'm going to test with 10 are possibly the 1 with 14 there. We can try that, which as you can tell is going to be too big. 10 times 14, too big to get to 31. Or the 7 with the 2. This one's at least possible. Let's try it. Negative 20 plus 7, now negative 13. No, that one didn't work. So, okay, looks like 10 and that didn't work. So I technically only tried one thing with the 10, and I might only try one thing with the 5 and the 2 as well. Now, the 2 is now the one that can't have the even number common factors, the 2x here. So here I can't put 14 or 2. Those have to be excluded. So possibly 14 and 1, and this isn't out of the reach because this one here, that's 28. That's not too big. So 28... Oh, minus 5. Okay, that's 23. And the last one to try here is the 7 with the 2. Let's try that one. So that's negative 35 plus 4. Okay, so I tested 3 things. Oh, you know what? Is that the answer, though? Negative 35 plus... That's negative 31. We need positive 31 here. So there we go. Okay, so I tested 3 things there. Some of them I kind of hit, obviously. Like, oh, never mind. That's not going to be it. But that's okay. We still tested it. It worked out. It was down to the last thing to test, though. You know, that happens. It's okay to test 3 things. Among, what could have we tested? Up to like 8. Like 8 different things, so we're all good. All right. 10n squared minus 11n plus 3. Once again with the 10 and the 3 here. So once again with the 10, it looks like we can't know for certain how things are going to work. Good thing 3 is a prime number there, though we can only swap the 3 and the 1. So let's check 10n. With n right here. No common factors with that 10 or anything to be as well. Other good news is this just minus minus because positive product negative sum. So either 3, 1 or 1, 3. Obviously the 3 can't go here because that'd give me 30. Too big. So let's try 3, 1. So that's negative 10 minus 3. That's negative 13. Doesn't work. Let's try 5 and 2. And again, if we put 3 here, it'd be too big. That'd be negative 13. So let's try 3, 1 here. That is negative 5 minus 6, and that's negative 11. So that works out. So I only tried 2 things realistically. It worked out. We're good. All right, and this one here, oh, this one is just straight up common factors, nothing else to be had. So I can factor out a 3 and a b. It looks like 3b, and I'm left with 3b plus 10. Hey, nothing else to do. As I said, guys, when it got to factoring, it ended up getting easier along the way because... I don't know, my colleague decided to go in reverse order with them. That's okay. We'll leave them. Okay, guys, we are now jumping into the next module of sorts. So with this module here, this is where we did, like I said, transformations of quadratics, cubics, and graphing polynomial functions, finding inverses of functions, composing a function with a function, composition of functions, I should say. Even in odd functions, and like I said, that doesn't appear on here. And I don't think I'm testing my students on even odd. I think, I don't know. I'm not testing them with it. So let's go into it, guys. We're going to find inverse of each function. Now, I'm going to have us do another thing on top of this. We will do composition of functions with this. So another instruction that I'm going to add here. I'm going to add this. I want to compose the function with its inverse and simplify to x to confirm it is an inverse. I don't really know. How about this? Compose the 2 functions. Compose the 2 functions and simplify to x. Now, there's reason I'm saying simplify to x. And it's probably, I'm speaking before I do it, so I hope that's okay. You know, because we're not doing this part first. We're going to do this part last. We got to get the other one. But when you do a composition of functions with some function and its inverse, what happens is it should simplify to become simply x. And then you know it's an inverse there. So we will do the composition thing to confirm, but we first have to figure that out. So this is one problem and then another. They're completely independent of each other here. So I have f of x equals negative 2 plus x minus 1 quantity cubed. To find the inverse of the function, what we do, I'm going to change f of x to a y. It's just more... It's more algebraically appropriate when it comes to manipulating equations. So what we do to take an inverse, guys, in order to take this inverse here, I'm going to swap the x and the y. Once I've swapped this, we have now applied the inverse here. But what we have to do is get it in a function notation, if you will. We have to get y by itself again. So we're going to do everything in our power to get y by itself, and it involves the following. Y is being subtracted by 1, that quantity is cubed, and negative 2 is being added to the whole bit. So in getting y by itself, let's go ahead and add 2 to both sides. I don't even need to put that. I'm sorry, you know what I'm doing there. Add 2 to both sides. I get x plus 2 equals y minus 1 quantity cubed. I will put this step, though. Let's take the cube root of both sides. That is what's going to cancel out the little cubic part right there. The cube root of y minus 1 cubed will give me y minus 1. And here I'm going to have the cube root of x plus 2. Now, if I add 1 to both sides, I'm going to put the y on this side if you don't mind. If I add 1 to both sides, I'll get y equals the cube root of x plus 2. And then there's the plus 1 that I added to this side. And there would be, essentially, my answer. Now, I'm going to instead write it in inverse function and inverse notation there. So inverse of f is the cube root of x plus 2 plus 1. We haven't seen these in a while as far as what they mean. I'm not going to get too deep into what it means, but graphically, they reflect over the line y equals x. You kind of see a reflected version of it. All x's become y's, all y's become x's. Here's the inverse that was asked for when they asked you to find the inverse of each function. Let's do the second instruction now, though, as well. Let's compose the two functions and simplify it to x. It's gonna, once I simplify it all, it's just going to turn into an x. In that way, we will then confirm it is an inverse. And because I'm already going so long in this video, let's just keep going longer. I am going to do both f of the inverse of x, and I'm going to do the inverse of f of x. I'll compose both and confirm that you get it in both directions. Actually, is it viable for me? Yes, it is. Okay, let's go ahead and let's do f of the inverse of f of x. Now, what this means here is I'm going to be using my f of x function here, but in place of x, I'm going to have this expression. This expression right here will take x's place. To make it a little bit better, we do know that f of x equals this whole thing. So instead of, inverse of x there. So right here, I'm going to put, instead of that little inverse thing, I'm going to put that thing, cube root of x plus 2 plus 1. You have to remember, guys, x is nothing more than an input. And when we look at function notation, this represents the input. So this will replace our input right here. This replaces x. So I'm going to write negative 2 plus quantity instead of x, this minus 1 cubed. So this is negative 2 plus the quantity, here we go, cube root of x plus 2 plus 1. And then there's the minus 1 cubed. Okay, and if all goes well, which it shall, will be hunky-dory. 1 minus 1 is 0, so those are gone. So as far as just getting a cleaned up version of what we have right now, that's negative 2 plus, not very clean, plus the cube root of x plus 2, and that's cubed. Well, what happens when you cube a cube root? Those cancel themselves out as well, and you'll just be left with that x plus 2 there. So now we have negative 2 plus just that quantity there, just the x plus 2. And now I have negative 2 plus 2, which is 0, and we are just left with x. So we have just confirmed by using that we got x by composing those two functions. And we should, whenever we have a function with its inverse. When we compose a function with its inverse, it should simplify to just x. Okay, let's go ahead and do that again, only this time. And you, for my students, just do this once. Do it once and you're good. Now let's do the inverse of f of x this time. So now we're going to be doing the inverse of, what's f of x? Negative 2 plus the quantity x plus, x minus 1. Negative 2 plus the quantity x minus 1 cubed, I believe. Let's, negative 2. Yeah. Okay, so this is going to replace, this is now going to replace x inside here. So I'm going to use the inverses equation, and I'm going to insert this expression for x in its equation here. So here we go. We'll get the cube root of, and instead of x, I'm going to write this, negative 2 plus x minus 1 quantity cubed. And there's a plus 2 inside that function, right there. and then plus 1. Actually, there's no guarantee that's a function in other circumstances. So here we go. We have a negative 2 plus 2. By the way, these can't cancel right now. These can't cancel right now. You got to make sure all the other terms are kind of cleared out before you do that. So that's what I'm doing right here. And that's what I did before. I couldn't cancel this and this right here. I have to first cancel those out. Negative 2 plus 2 is 0. So there's that cancellation that we have, the effect. So this is the cube root of x minus 1 quantity cubed, and then plus 1. Now we can take the cube root of the cubed quantity, and those are gone. And then we get, so now it's x minus 1. So that's x minus 1. And here's plus 1. And negative 1 plus 1 is 0, so you're just left with x. So we are all confirmed up that we got, once again, composing the two functions, one with the other, that we do get x, which means these are indeed inverses. Okay, so I did it correctly, and I kind of showed it twice for that. And we're going to do the same thing for number 24. Now, I'll let you know once again that as this time racks up, guys, I didn't do the composition of function things when I did my 14.5 minutes. So these are parts of the times that are racking up kind of on their own as a nature of, I think these are relevant for what my students need to pull through. I'm kind of glad that I did do the practice test before. Normally, I like that plausible deniability, going in blind and, working it out with you, strategy, saying here's what I would do. But, yeah, no, we're good. All right. F of x equals negative 1 over x plus 2 plus 3. Now, I just want to let you know here, some people really have trouble with negatives and fractions, meaning where this negative kind of goes or can go or things like that. If it helps you just a little bit here, I'm going to take this negative and I'm going to place it right next to the 1, just to kind of give you the idea that, guys, a negative only applies once in the fraction here. And I'm just going to place it there just for good measure right now so you can just see. Okay, the 1 is negative. Okay, let's feel it out like that. All right, let's start by taking its inverse here. And in taking its, let's make that black. Hold on. There we go. And in taking its inverse, first let's change the f of x to a y to make it a little nicer looking for us. And now let's do the inverse. Let's swap the x and y, and then we'll go ahead and solve for y after. Okay. Now, in order to do this, we got to get y by itself and in the numerator. A couple things there. We got to first subtract 3 from both sides, and then kind of deal with that fraction the way we do. X minus 3 equals negative 1 over y plus 2. Now, people have some trouble with this step right here, and I hope that me speaking on this, you can go back to the other inverse stuff, and I did this before. I'm going to multiply both sides. Listen, I got to get y in the numerator. It's one thing to be able to move everything else over on the other side of the equation, but this would still just say 1 over y. I need to get y in the numerator. So I'm going to multiply both sides by y plus 2. At the same time, if it makes things easier, I need to get this out of the way here. So I'm going to divide both sides by x minus 3. So the y plus 2's gone, the x minus 3's gone. What happens is the y plus 2 and x minus 3 switch places. That's not really an algebraic way of putting anything, but they do. They switch places. Now I have y plus 2 equals negative 1 over x minus 3. They switch places in what I worked out. There are a lot of other ways I could have written that. I could have done proportion, cross multiplication, things like that, saved one step over the other. But in the end, these two things had to happen. Multiply both sides by y plus 2, divide both sides by x minus 3. Or if you know the magic steps of switch places, when you can and when you should, that's fine. Anyway, now I subtract 2 from both sides, and then I'm going to get, where should I write this? I guess right here. I'm going to get y equals negative, I'm going to put the negative right in front again. Negative 1 over x minus 3, and then minus 2 like that, or the inverse of f equals negative 1 over x minus 3 minus 2. So there's its inverse. There's its inverse right there. Compose the two functions. Okay, not going to be as fun with this one because we're going to have fraction within a fraction no matter what we do, but I am committed. It's something that you got to, it's not fun. That doesn't mean it's not possible. So, let's just go ahead and, do it. You just got to do it once. I'm going to have to do it twice. Oh, dearest to me, what did I get myself into? All right, so here we go. Let's do f of the inverse of f here. So that's going to be f of negative 1 over x minus 3 minus 2. So this is going to substitute for x here, okay? So that's going to be negative 1, and I'll put the negative 1 on top there. Negative 1 over, so instead of this, I'm going to have this. Instead of x, I'm going to have negative 1, hold on. Instead of x, I'm going to have negative 1, all of this is a negative 1 right here, over x minus 3 minus 2. Now there's a plus 2. Oh, this won't be too bad. Plus 3. You just got to follow along with me here. So there's a fraction within a fraction, right? This whole thing is quantified down below in the denominator, yada yada. Now, I have a negative 2 plus 2. And once again, this is important to take care of first. Negative 2 plus 2 is 0 because now I have a straight up dividing by a fraction. So this will be, and you know what, the same thing, honestly, the same thing's going to happen in the other version. Maybe I will just do this once. And it is good that I put this negative with the 1 here. So this is negative 1 over, and in this, here's a fraction, negative 1 over x minus 3 plus 3. Now, there are some things that people want to be inclined to do at this stage. Oh, geez. Including canceling some things out, which is actually kind of possible to do. But I want to make sure you know how the division by the fraction works in this instance here. So this would be, so negative 1, I want to put this in a way that makes best sense to you. This over fraction means it's division, right? I'm going to do left to right division, like division divided by this negative 1 over x minus 3, right? That's what it's dividing by, and there's a plus 3. You know, when you divide by a fraction, it's the same thing as multiplying by its reciprocal. So that becomes negative 1 times x minus 3 over negative 1. So I flip this as I multiply. Now that negative 1's dividing with that negative 1. And there's the cancellation. But more importantly, x minus 3, the thing that was in the denominator of a fraction that was in another denominator, is now in the numerator. X minus 3 has risen from the ashes and has come up here to save the day. X minus 3 plus 3 will go bye-bye. Negative 3 plus 3. Let me save that one for the next thing. But they will go bye-bye here. It's x minus 3 plus 3. Go bye-bye, which is just x, as those ones cancel out right there. All right. And there's that one. You know what? I think I'm going to stick with that one because I'll be honest. The other one's going to feel so similar. See, these two didn't feel, I mean, these feel, you know, they felt somewhat, I guess, whatever. But we did the cube root of something cubed, and we cubed the cube root of something. Here, we're still going to have the fraction within a fraction, and nothing really is going to change on that front. You'll still see the exact same steps of multiplying by the reciprocal and stuff. So I'll leave it to that. I compose one function with the other. I hope that you are very, very happy with what I did there. All right, let's move on to number 25. Okay, now, with some of my classes here, I made mention of, let's change the problem. Let's change the problem. When I graphed this is part of the 14 minutes, whatever. When I graphed this thing, I said, this is not a good graphing problem, at least given the axes and stuff. And by the way, the graph in the PDF that you have is unfortunate too. It goes by 2s, and I don't have a way of changing that now in that digitized form. But right here, I changed my graph for my own sake. So I hope you can make do the way that you need to when it comes to graphing it. At least follow along and feel comfortable. But I'm changing this graph actually in full. I'm going to get rid of this negative 5 completely. I did feel like doing something with a fraction or something like that, but I don't know. I didn't when I told my students. And I'm changing this to an x squared. And change this to an x squared. Yeah, I'm doing less when it comes to describing transformations and stuff like that. We are going to do 2 other cubic graphs. I believe their graph axes are a little bit better as well. But I want to do a quadratic, and I didn't want to deal with something just so large. I probably should have put in a fraction, but that's okay. All right, so we have g of x equals x squared, and let's describe, I never read that, describe the transformation done to it to produce the new function f of x equals there, then graph the function with a capital G. All right, so let's go ahead and do that. So first, let's describe this thing. There are only 2 things we're going to do now. See, before, just so you know, with that negative 5, before these things were going to happen, we were going to reflect g of x over the x-axis. It was going to flip over, and we were going to vertically stretch it by a factor of 5. I'll deal with the vertical things that we have in the next graphs that we have. But here, we are still going to translate g of x 5 units left. That's what h is doing. And 7 units down. This is assuming you've seen this before. Our whole thing, if you can bear with me here, our whole idea of these graphs are, I don't know if we're f of x, I'll just write y. Y equals a, geez. Wait, how did we do, well, we had g of x, okay, for a quadratic, y equals a times x minus h quantity squared plus k. I'm ignoring the b stuff right now. I don't think we're going to be dealing currently with some horizontal stretches and compressions. I think I'm done talking with those for a moment. So here, this is our vertical stretch compression. This is our vertex point, HK. And remember, the subtraction here means that we're going to be doing the opposite of what's there. This is a 5. We're going to go 5 left. This one, as a plus, means whatever this minus is, will just follow. Minus, let's go down. All right, so let's go ahead and graph this thing here. I'm going to translate my vertex from the origin. I'm going to go 5 left, and let's go 7 down. And again, this will be different from what I graphed earlier here. Now, graphing a quadratic here is going by the nature of the quadratic. There is no stretch factor that we're going to apply, so let's just go by quadratic nature. From the vertex, let's translate. Let's offset this. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. And I'm plotting as many points as I can possibly fit here. What I'm doing is 1, 1, 2, 4, 3, 9, 4, 16. I'm going by the nature of a quadratic graph and what we're going to do with that. And I'm going to do that with the cubic graphs as well, only I think they have fraction a values. We're going to deal with that. And we reflect right here. This goes 1 over the axis of symmetry, 2 over here, 3 over, and 4 over. They're equal height. And this will make a very beautiful, progressively curving quadratic graph by nature. I much prefer this problem over what I had previously because that last one, man, it really just did not help you provide what it is we're trying to do with the graphs just because the -5. I'm sure I could have made do in a better way, and this is just what I did on the fly with my kiddos. So there you go. Let's get a quadratic in. We got it right there. All right. I got 4 more problems to do. All right, a general equation for a cubic function is y equals, oh, here, perfect, there's the general function there. Write a specific equation for the function shown below. So now we have to come up with basically the a, h, and k. There's more than one way to do these problems, guys. There's an algebraic way to do it, but I'm going to stick with the nature of us understanding how these graphs work. Let me first write out, if you can think of that quadratic there, as I talked about, 1, 1, 2, 4, 3, 9, etc., how that thing's going on. X cubed graphs, we cube 1, we get 1. We cube 2, we get 8. 327, 464. My students should know this now because some 2 cubes and things like that, right? 1128 occurs here naturally with a cubic function. Now, I'll get into that. Let's first talk about the h and k here. This is our center, our reference point here. It's not a vertex, but it's a center. This point is at 5, -1. That means that h is 5 and k is -1 right there. But we have to figure out the a value now. Now, the a value has to do with what I'm talking about in the 1124 stuff, or 1128, I should say. Naturally, a cubic function would go 1128, and things like that. But this one seems to be stretched a little bit. It looks like this doesn't go 1, 1. In fact, it looks like it goes 1, 2. It looks like that got doubled. The vertical stretch got doubled there. Or 1, -2, as cubic functions will also go negative that way. And I can't fit this, but I can imagine this is going to 16, going up there. So now that you see that it's a 1, 2 instead of a 1, 1, what you're telling yourself is we're doubling that. We're doubling that height. You know what? That means the a value is 2. And that's what we got to do. We just got to recognize instead of 1, 1, it's 1, 2. The a value is 2, and that can help us make our equation, which is y equals 2 times x minus h minus 5 cubed plus k is -1, and that is our equation. Yeah, there's an algebraic way to do it as well, where what you do is you substitute your hk. You still have to find that hk there. There's our hk. And we plug in this as an xy value, 6, 1. Substitute it into this general form right here, and you use it to solve for a. You should get a equals 2. You want me to do it fast? Fine, let's do it fast. xy, hk, y is 1, a is unknown, x is 6, minus 5 is cubed, plus k is -1. 1 equals a times 1 cubed minus 1. 1 equals 1 cubed is 1. A minus 1, add 1 both sides, a equals 2. And you know what? That's one of the easier ones, probably one you're better off with there. And we get that 2 value there. All right, here we go. 3 more problems. 27, 28, let's graph. Here we go. Here are the cubics. And I wish that they got a little more versatile with these, but versatile enough. Now, as far as the form goes, right, keep in mind this form we're talking about, a times x minus h quantity cubed plus k. We got to identify our a h and k here. Now in this first problem, a is clearly negative 1/3, and we'll talk about what that means in a second. But there is no quantity here that's being cubed, it's just x. That means the h value is 0. There is no horizontal translation to this. But the k value is also clearly a negative 2. There's a vertical translation. So what we're going to do is we're going to translate this center 2 units down. I'm going to go 2 units down right there, and that's the center. Now, the basic nature of the graph, just to kind of remind you, these are not going to be the official points, but the basic nature of a cubic is 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8, if I could fit it, and there would be a graph that, does that. Now, that's not our graph because we have an a value of negative 1/3. The negative flips it over, reflects it over the x-axis like this instead, but the negative, but the 1/3 also compresses the graph. It divides everything by 3. We take 1/3 of everything that we had. So instead of 1, 1, we're going to go 1, 1/3 of 1, which is 1/3. We divide it by 3. Instead of 2, 8, we're going to go 2 and 1/3 of 8, which is 8/3, which is 2 and 2/3. So down 1, 2, and 2/3. And if you don't really know that point, that one's kind of fine. I think you should be able to do 1/3, but 2 and 2/3, eh. This one's going to be kind of nice though. Let's fit this if it can fit. I don't think it can officially fit, but that's okay. 3/27, right? 3 cubed is 27. Let's take 1/3 of 27, which is 9. So 3, 9. Now I can't really fit that. That'd be like 9, 10, 11. It would be like down there. But I can fit it when going up, and I'll be sure to do that one. That's close. That's probably it. So kind of, not reflect, but let's kind of go upward. 1, 1/3. 2, 2 and 2/3. And 3, 9. So all the way up to the 7 right there. That one does fit. So these are enough points for me to be able to draw this graph right here. Let's go ahead and give that one a shot as we curve. Oh no. Oh dear. Oh boy. Let's try that again. So we go down. I should really just edit this out and fast forward it. I'm guessing you're drawing it at the same time though, so that's okay. Not the best, not the worst. All in that second try. Okay, number 28. Let me move myself just in case I need room to talk about stuff. I don't need room. Who needs room? All right, graph. It's another negative here and another fraction. See again. I wish that they got a little more unique with these. All right, your a value is negative 1/2. That means reflect and vertically compress by a factor of 1/2. Our h is negative 2. Remember, opposite of. And our k is negative 1. It seems like we're always translating downward. So negative 2, negative 1 is our center. That's where we're going to go right there. A being negative 1/2, remember, reflect over the x-axis, so we're going to go this way. And the 1/2 means we'll divide our values by 2. So instead of 1, 1, let's go 1, 1/2. Instead of 2, 8, let's go 2, 4, half of 8. So 1, 2, 3, 4. And that's really all I can fit. I can't go down 13 and a half, which is half of 27. All right. 1, 1, nope. 1, 1/2. 2, 8, nope. 2, 4. Really all I can fit there as well. All right, so in this cubic function here, it's going to have a little sharp ascent thereafter. But let's go ahead and fit what we can with that. It's that looks rough around the edges. Let's try that again. All right. Same thing. By the way, I mentioned this to my students before. I'm going to mention it now. Never go fully vertical. Do not bring this straight up. Do not have it bend backwards and over. Never go fully vertical. And definitely don't let it bend back this way, right? I don't mind you working it in a seemingly linear pattern. It's hard to tell what it's doing after that when it starts steepening like that. Never go fully vertical. That's not a function. That's not how that works. X's keep increasing in both areas there. All right, those are those two graphs there. All right, 2 more problems, and I believe they're both polynomials now that I remember. And I'm going to include some more information for you guys over on the side after I graph these, okay? Let's sketch a graph of f of x equals x cubed times... I'm so glad I just need to mention this. I'm so glad I did not realize that I wasn't recording at this point. I would have just ended up not making a recording. Sorry. Or I would have said, deal with what you have. No audio. Sorry. All right. Sketch a graph of f of x equals x cubed times x plus 3 times x minus 6. So, few things. Although we aren't doing zero product property so much right here anymore when it comes to solving, consider the fact that if I set y equal to 0, then we can find our x-intercepts. So if I set it equal to 0, the zero product property states if this times this times this equals 0, then either this equals 0 or this equals 0 or this equals 0. Now, what I just found here, these are x-intercepts. These are where they cross the x-axis. This is what this polynomial will do as well as a full f of x thing. These are the zeros of them, so this is where they cross that x-axis. So they didn't really give it, they gave us wiggle room to be able to do what we do here. I need to make sure I reach 6, and 6 I shall reach, and at least -3, but just to keep it even. I'm not so concerned right now about the heights necessarily. In a different class, I actually would be. With a different curriculum. We talk about y-intercept, we talk about some of the mins and maxes and some points that can cross for sure, get some different a values. But here, no, we're fine. We just got to figure out where these things cross and the end behavior of it, which is some of the things I'm going to have us list in a bit. So here are some points that we have. We know that x will cross at 0, -3, and 6. Now, a couple things here. Number one, where x equals 0, you can tell that this said x cubed. That means that x equals 0 has what's called a multiplicity of 3. Multiplicity of 3 means that when it crosses through here, it'll behave very cubically. We just did cubic graphs, and this is what they did when they go through. It'll behave that way. It'll still go through, but it'll have that curvic behavior to it. Second thing, this is a x cubed times x times x. It's an x to the 5th function. It's a positive x to the 5th function. Odd degree functions have a nature of starting one way, finishing the other way. And when it's positive, it will start down, finish up. So this graph is going to start from underneath down here, and it's going to end up finishing up here. Now, what does it do in between? Well, pretty simply, it passes through this one here in a linear fashion. Let me just kind of bring that down. Passes through this in a linear fashion. It hits some sort of relative max, I don't know where, but it goes back down here and it hits through this in a cubic manner, right there, and it's going to hit a relative minimum of some sort, and it's going to come back up through there. Whoa, almost went vertical. I kind of sort of did. Let me kind of change that because I don't want to undo that whole thing. Let me just erase that. So there we go. There's the graph. Let me get the other arrow going. There's some version of that nature of that graph, which is just beautiful, guys. It's just so elegant. And there we go. There's our graph. So let's start getting some more information out, if you don't mind. Let's talk end behavior. We just did, but let's do it in a more official way. End behavior. So as x approaches infinity, I don't have to, oh, you know what? Let me just handwrite it. Sorry. All right, here we go. As x approaches infinity, as x goes forever right, what are the y values doing? Well, they're going forever up. Y approaches positive infinity. As x approaches negative infinity, as we go forever left, we see the y values forever down. Y approaches negative infinity. So there's our end behavior of that graph. Okay. I'm trying to think what else we talked about. And we talk about these things. For example, this is what's known as a relative max or a local max. This is known as what's called a relative min or a local min. There is no absolute or a global maximum or minimum because it goes up forever and it goes down forever. This is not, right? This is not an absolute min. It goes lower than that. This is not an absolute max. It goes up higher than that. So there's no absolute max or min. The x-intercepts, right? These three here, these are the x-intercepts, 0, -3, and 6. This one had a multiplicity of 3. I'm not going to talk about intervals of increase, decrease, positive, negative, things like that. But I'm not going to write notations here. But you can tell it's negative until it hits -3. It's positive, and positive, I mean above and below the x-axis. It's positive until it hits x equals 0. It's negative until it hits x equals 6. And it's positive the rest of the way. So there we go. Okay, I think we kind of covered all that I feel like I'd want to cover there. We're good. Let's go forward. Last problem, guys. Number 30, sketch a graph and do all that jazz. So let's do the same thing as we did before. Let's come up with the x-intercepts. And it's really all about setting y equal to 0, zero product property. Basically switch the signs. Now this one is just x equals 0. X equals 0 is one of them as that one. Some people would put like 1 or something like that. No, that's 0. When x minus 2 equals 0, x equals 2, right? Switch the sign. Now this one has a multiplicity of 2 as well, because the squared thing. We'll talk about that with the graph. And then lastly, x equals -1 on that one right there. So let's go ahead and fit those. I think these can go a little bit wider, as we just have to hit 2 as far as 2. Okay, so let's plot this at 0, 2, and -1. Now let's figure some things out. This is an x times x squared times x. This is an x to the 4th function in even degree, but furthermore it is negative. It's a negative x to the 4th function. So even degree functions either start up, finish up, or start down, finish down. This one, being negative, will start down, finish down. That means it's going to start from down here and it's going to finish down here. What it does in between, let's figure that out. These things will pass through linearly at -1 and at 0. So it'll come up from the bottom here, pass right through -1, hit a relative max, pass through 0. Sorry, let me do that kind of less, more smoothly. Go through -1 here, and then pass through 0 here. And then for it to finish down, remember, when it hits 2, it has a multiplicity of 2. It's going to bounce off like a parabola. It's going to hit once, bounce off there, and it'll finish downward. And that is a nature of that graph that has that even degree relationship, has the multiplicity of 2 at 2. And there we go. There we have it. Okay, we have the x-intercepts. Let's talk end behavior. Whoops. And end behavior will state, as x approaches positive infinity, y seems to approach negative infinity. As we go forever right, we're going forever down. And as x approaches negative infinity, y approaches negative infinity. This is once again one of those things that I didn't do in my 14-minute little speed run. What else did we talk about? Oh, I mentioned relative maxes and mins. Here's a relative max. Here's a relative min. Here's a relative max. Don't forget intercepts are relative, potentially relative maxes right there. It's negative, positive, negative, negative, and these are the zeros. There is an absolute maximum. This thing here would also be an absolute maximum in that it's the highest that the graph ever goes. I don't know what it actually is, but it doesn't go any higher than that. There are chances where, you know, like what if this one went up and down? Which one's the max? I don't know. But the thing is the graph has an absolute max. It's not just that this is it, but it has one. No absolute min as it goes down forever. Okay, I think that's all I can kind of cover there. And that ought to do it for this one, guys. So the hour, 20 minutes, as you can tell, I stated this would be more than an hour. Obviously, I did more here than I did for myself. But, you know, consider that speed run to be a nice version of efficiency, that 30 problems in 14 minutes ain't too bad. Something that you guys can do as well if you just kind of open up your mind to the strategies that we're doing here. That's why this dialogue's here. I hope that this was all very helpful for you guys. This is Mr. Robinson. Good luck on all that you do, and take care.